As explained, I'm Jason Hyon from JPL. I've been working at JPL for 40 years and doing kind of management of technology for 25 years. So I have a pretty good understanding of what it takes to mature technologies for space applications. Before I get into the specifics of the quantum sensor, let me just quickly go over kind of basics of quantum capabilities. So what is a quantum sensor? Basically utilizing quantum phenomena such as a superposition, entanglement to measure a physical quantity, such as acceleration, rotation, and gravity of extraordinary precision. So instead of using a classical microwaves and mass as a key way to measure other phenomena, you're using atoms. Oops, somebody has a live mic. Photons and molecules to uh, have a higher sensitivity and be able to miniaturize because these systems are very tiny, so you can miniaturize it, but also order of magnitude sensitive systems. So we can utilize these quantum phenomena to build a measurement system. And what you see on the bottom is something called the Cold Atom Lab. This is currently operating an International Space Station. Dr. E should know. Because it's operating an international station, we can upgrade these systems. So it's been upgraded at least 4 times. And this is working as a facility, so many physicists can buy time and be able to do demonstrations. And this is first in space to reach Bose-Einstein condensate, talking about pico Kelvin type of very cold state, and be able to use that state to detect gravitational force, dark matter, and dark energy, and other experiments. So that's what the quantum system will do. And then specifically, we are using atom interferometer as a technique for changing mass. So if you want to look at large ocean circulations or ice melting or aquifers underground, these kind of quantities you cannot detect easily with a classical system. And if you want to detect those phenomena, you have to kind of detect the mass change, and those mass change will have a different gravitational force. And in a classical way, we fly two pair of a satellite in tandem. And basically, you're constantly measuring the distance between the two. And as you move between different mass, either the spacecraft can be pulled together or pushed apart. And by measuring the distance between those, you can derive the mass change underneath that you're flying over. And by utilizing atom interferometer, you're basically cooling a two cloud of atoms to a very stable state, and then doing a shining light to spatially interfere each other. And same thing as you fly over different mass, these cloud of atoms will move and shift, and by measuring those, you can also drive the mass change. So that's the kind of techniques that we're using to develop a remote sensing capabilities using quantum phenomena. So based on these type of breakthroughs, and there's a significant government investment, as you heard of quantum information science initiatives done by White House. They're putting in about $1.5 billion in past 3 years. And there will be more investments going into this area, especially in the quantum computing, quantum networking, and quantum sensing. So, as a JPL being the only NASA's research lab, our main objective is to demonstrate first of a kind in space. So we think that quantum sensing is something that's going to play out in the future for both growing markets and then also enabling new missions for science. For NASA, I took up on a responsibility to form a Quantum Space Innovation Center. And basically, the role of that center is to harness and leverage breakthrough quantum technologies. And then also, as a part of the center, we create a hub, quantum hub, and the hub consists of industries and university partners so that we can help them grow new workforce, giving them training opportunities and internships so that we can take advantage of these next generation workforce in the advancing quantum technologies. So as I said, these are the three key areas that JPL is interested in. One is developing applications and kind of critical components that goes into building a quantum computer. And then also many applications in quantum sensing, and then also quantum communication, be able to connect multiple quantum computers on the ground through free space optical link through spaceborne capabilities. So those are the kind of three main areas, and we're leveraging a lot of these different quantum technologies, lasers, integrated photonics, many different devices that's been developed for many different applications, and we're kind of pulling that capabilities to miniaturize and ruggedize it for spaceborne applications. That's the main purpose of the center. And why JPL compared to all other NASA centers? JPL is the only center who actually flew quantum sensors in space. So like I said, started in 2018 with the Cold Atom Lab. We flew Deep Space Atomic Clock. In 2019, it's based in helium-ion clock. And we also demonstrated entanglement experiment in International Space Station called the QSIC in 2024. We're currently developing a quantum gravity gradiometer. This is the atom interferometer to detect mass change, and we're scheduled to fly this in 2030, so 5 years from now. We also developed superconducting nanowires, single photon detectors. These are single photon detectors that can be utilized for both quantum computing and then quantum inner network from space. And then also microwave kinetic inductance detectors, and then also miniaturized sensors of these capabilities. So these are all ongoing activities at JPL. Obviously, with many partners. So we have a lot of industry partners helping us developing these capabilities. And not only that, we also have about 12 different test beds that can do ground experiments, cold atom test beds, entanglement test bed for optical links and communication, atomic clock test beds, laser optical systems, and we also have a micro devices lab that can grow wafer level capability all the way to subsystem system level capabilities. So if any of you are interested in working with us and bring in your specific component and wanted to understand how the system works as a whole, you could utilize this test bed to test your components. And as I said, the Quantum Hub is a consortium of universities. Right now, our members consist of Caltech, obviously, USC, UCLA, UC San Diego, Santa Barbara, Berkeley, and Arizona State and Arizona and Colorado. So we're happy to have more. So I think University of Maryland is interested in joining, University of Illinois, and then some of the schools in New York State. So we're continuously growing, and then basically the key is we want to give out seminars. We want to teach them how to ruggedize this system for spaceborne applications. So there's a flight schools, and then also during summer we can offer internship opportunities, and then basically entice students getting into this quantum applications and technologies to be interested in, enabling science missions using these techniques. To be honest, most of the workforce that we currently have are all mostly from Europe. So we don't have many US-based students or people working in this field. So it's very critical that we grow US-based workforce in this area. And as for quantum capabilities concerned, in the device level, like I said, the detectors, various detectors that utilize quantum phenomena. And then as far as the subsystems concerned, optical terminals, the chip-based atom trapping capabilities, or a fabrication of those atom traps, control electronics for various systems that we're operating, and then solid-state lasers for spaceborne applications. As far as the sensors concerned, we're developing magnetometers, gravity gradiometers, Rydberg microwave sensors, optical clocks, and then quantum algorithm processing. And basically, in the future, we want to be able to create a entangled spacecraft with the sensors in a way that it is a constellation of quantum sensors that can significantly improve the measurement quality. I'm going to quickly go over some of the examples that we're currently implementing. So first one is quantum communication. Basically, we're going to do quantum key distribution from the ground terminal using free space optical link to a LEO satellite and be able to downlink to another ground terminal. And basically, by connecting two computer terminals, you want to be able to connect two quantum computers seamlessly using this QKD architecture. And here are some of the component level or subsystem level demonstrations that we have done already. SEEK is the one that we already told you about in International Space Station. DSOC, we were able to demonstrate 1 AU distance and be able to do 1 gigabits per second transfer between the spacecraft and the ground terminal. The Octo is a telescope at near JPL to downlink a station and uplink. And then SSPD is the single photon detector. This is a critical part of the sensor package in order to do entanglement of entangled photons to transfer from the ground to the space. And then also demonstrating the full space quantum network demonstration. Like I said, the DSOC, we're able to downlink from 1 AU distance. This is currently on Psyche mission. We have a deep space optical communication payload that's flying. And then we're able to download this cat video to the ground, just to have some fun with the Schrodinger's cat experiment. And we're going to be using these as a baseline for enabling future quantum communication. And by the way, Korea, CASA is very interested in having a L4 mission. And on that L4 mission, we'll be working together in enabling optical communication from that spacecraft using this technology. And this is kind of the ultimate goal for establishing a quantum communication from space. Basically, from Caltech to JPL, we're able to demonstrate an entangled quantum network demonstration already. It's about 6 kilometers in the thick atmosphere, which is equivalent of transmitting a data from the ground to LEO orbit about 400 kilometers. So we're able to demonstrate that. And then we're also doing experiment between JPL and Mount Wilson. It's about 1.5 kilometers above the ground. So we're able to do interferometry with the gravity phenomena. And then also, once we have the on-orbit satellite for quantum key distribution, we'll be able to communicate between that satellite and our Table Mountain optical telescope. And then ultimately, with this key infrastructure and demonstration, we'll be able to establish a quantum communication between Earth and the moons for the human exploration. I'm not going to spend too much time on this because the time constraint, but like I said, that we're able to achieve about 1 gigacounts per second with this technology. And our goal is to not a single photon sensor, but be able to do an array so we could receive multiple photons at the same time. And the key aspect is not only the sensor itself, but we need to have a very high efficient cryocooler. Basically, currently it has to operate a 4 Kelvin. So, miniaturizing and ruggedizing this 4 Kelvin cooler for spaceborne application is one of the critical challenges that we need to overcome. And that's what we're working on. As far as atomic clock's concerned, we, like I said, demonstrate a helium ion clock. It's about the size of a couple kilograms. It's right now we're able to further miniaturize it in the size of a penny that goes into every single tactical aircraft. And we're continuously improving the clock stability from 10 to the minus 14 to about 10 to the minus 18. And once you get to that stability level, you could actually do fundamental physics experiments like dark energy and dark matter detection, and also gravitational force detection. So we're geared towards building a very high stable atomic clock using strontium and yttrium. And then also we're developing, we're comparing that and mitigating those clocks for spaceborne applications. I think I covered that a little bit. Quantum gravity like I said, the one advantage is, two people 2 meters apart walking across each other. That's the kind of force you will feel. And what we try to achieve with this quantum gravity is 100 micro advantage. So it's very highly sensitive gravity detection payload. And once we've done the technology demonstration, we're going to build a science grade instrument, and the science grade instrument will achieve about 10 micron advantage accuracy. And once we get to that level, you could detect tunnels, you could detect submarines underwater, and then also because it's not relying on GPS signals, now you can fly these for other, ocean giants, ice world, in the other planetary bodies, and be able to see underground, underwater, under ice structures. So that has a lot of potential applications using this technique. Another sensor we're developing is called a Rydberg microwave sensor. Basically, using a cesium or rubidium, you excite the atom to Rydberg state, and once you reach the Rydberg state, any incoming microwave signals, whether it's a C-band signal, X-band, L-band, or UHF signals, with a single cell, you can receive all the different signals at the same time. So imagine each single radar, like C-band radar, is the size of about 1 meter by 1 meter by 1 meter. And if you want to kind of measure the whole vertical structure of a vegetation, top of the tree, density of the tree, bottom of the tree, soil moisture, and deep root soil moisture, you need to have at least 5 different radars flying at the same time. By having a Rydberg sensor, a single receiver can measure all the different frequency and vertically resolve the full 3D structure. So there's a significant benefit of using this technique. And we're able to already demonstrate on the ground using XM radio signals and other UHF communication satellites, and then also Ka band and X band. And our goal is to fly and miniaturize this system to airborne and then be able to fly this in a couple of years, and then ultimately fly this in space. And lastly, we also develop vector helium magnetometer. Basically, you excite the helium to optically pump it to a certain energy level, and the magnetic field will vary the energy level. And so that once the light is going through, it perturbates, and thus you can translate the 3D magnetic field effects. So it's very small, miniaturized, regularized system. And you don't need to have this long boom with the magnetometers at the end for a spaceborne mission anymore. By having this miniaturized system, you mount 3 of those on a spacecraft, and you can fully characterize the magnetic field. So there's a significant benefit of, once again, by miniaturizing it, and then also gives you high precision measurements. So these are some of the examples that we're advancing, and we're very excited about the future. And like I said, there's a lot of investments going on in quantum computing, and a lot of technologies are being developed, and we want to utilize these technologies and techniques and apply for spaceborne applications. And that's the main objective. And I hope some of you are very interested in this, and we are very motivated to build partnerships, at least within the United States, to advance this technology. And there's a significant competition between United States and Europe and any other countries. So it is critical that we have a US workforce that's working on this area. Thank you for listening. Here's how to reach me. And we're, like I said, very interested in partnering with any of your schools and institutions.